All right, welcome back to AP Physics C, Unit 5, Rotation. So here we're going to look at rotational kinematics. So I'll just preface this by saying a lot of the stuff we did way back in Unit 1 also applies here. So how do position versus time graphs look like? How do velocity versus time graphs look? How do acceleration versus time graphs look? How do we go between the different by using derivatives and integrals? All of that will apply here as well. The only difference is instead of it being in a straight line, it's going to be rotating. And so it's going to change our variables, but the equations are going to look very similar, with the only change would be to the variables that we use. So what's going to happen is now, instead of objects only moving translationally, and translational motion is just simply linear motion, they're also going to be rotating. So some of the quantities that we'll be describing rotational motion, because remember, that's what kinematics does, is it describes the motion. The first one is angular displacement. So what that really is how far does an object rotate? It is measured in radians. So now you don't have to put your calculator in radian mode, because we treat radians as if it was like meters. So it's how far it moves on the circle. And that's actually the definition of a radians. It's a property of a circle that says, okay, if I were to move from point A to point B, how far did I move along a circular path? And then we have angular velocity. So angular velocity is the Greek letter omega. It's simply a curvy W, if you want to put it that way. Okay, I'm sure Aristotle is rolling around saying, no, it's not just a curvy W. Okay, that is measured in radians per second, and then the angular acceleration is alpha. Right, and it's measured in radians per second squared. So you could see, just like what we did before, right? We have a position, we change that with respect to time, right? So we go from radians to radians per second, and then we change our velocity with respect to time, which becomes radians per second squared. So what we just kind of talked about and described was what we call definition formulas. So formulas that define what the quantities are. So first one, angular displacement. Well, it's simply your angular positions subtracted, just like when we did straight line, it was delta x equals x minus xo, right? So it's the same thing. And then we have angular velocity, right? When we change position with respect to time, well, that has the equivalent of, right, delta x over delta t. So angular velocity is delta theta over delta t. And then you have angular acceleration, which is delta omega, not delta theta, over delta t. And remember, that has the equivalent of delta v of acceleration, so delta v over delta t. So there are equations that do relate linear to rotation. So for example, x equals r theta. You should have seen this equation in math class, because this is the arc length equation. In math, they call it S, but here we'll just call it X. Then you have velocity is r omega, and acceleration, you can kind of guess with follow the pattern, it's r alpha. Okay, so r meaning the radius. So if I have a circle, a tire, it has a radius r, and if it moves, right, that's what we're talking about. If we want to relate straight line to rotational, we just simply multiply our rotational quantity by the radius, and that gives us our straight line quantity. Okay. Now, something that you can also, so there are a couple other things that we probably need to address. So you may see the unit. So the SI unit is radians per second, but you may see, RPMs, or you may see something with revolutions. So one revolution is 2 pi rads, or you can call it 6.28. Because again, remember, here in physics, we want exact values, or we want approximate values, not exact values. You might have substituting pi, that's an exact value. So we can just round to 6.28. And then, you may have to convert between revolutions per minute and radians per second, where you go from like 1 revolution is 2 pi radians, and then 1 minute is 60 seconds. Or you can just say 1 radian per second is 9.55 revolutions per minute. And so with that one, you would need to make sure that you memorize that, because that's not something given to you. Now, way back in unit 1, we did the cake formulas where it was constant acceleration in kinematics equations. Now we have the constant angular acceleration in kinematics equations. So it's like saying cake, okay? But they're basically the same thing. The only thing is we're flip-flopping or switching out variables. So here is our quadratic, right? So instead of having v and x and omega, or v, x, and a, we have theta, omega, and alpha. And the one thing, remember, t doesn't care about if you're rotating or if you're moving in a straight line. So remember, this is actually going to be our, the quadratic is our, in this case, it'd be theta t graph. And then the next equation, omega equals omega 0 plus alpha t, would be our omega t graph, right? So the stuff we talked about graphing in way back in U1 is the same as we do here. And then we have our equation with no time. And then the one that the test does not give you. So again, just like what we did way back in unit 1, we talked about how there are 5 quantities and each equation has 4 of the 5. It's the same thing. So there are 5 rotational quantities, and so each one has 4 of the 5, right? So sometimes if you need to find, which equation you're using, then you need to just simply find the one that's missing and then fit the equation to that. And again, missing meaning not asked for and not given to you. All right, so let's look at an example problem and see how these equations would work. So here we have a deep sea fisherman hooking a big fish. The line's pulling. The whole system is initially at rest. The fishing line unwinds from the reel at a radius of 4.5 centimeters from its axis of rotation. The reel is given an angular acceleration. I'm sorry this got kind of messed up, but this is 110 radians per second squared. All right, it's going to do that in 2 seconds. So what is the final angular velocity after the 2 seconds, and how many revolutions does it make? So this isn't looking for radians, this is looking for revolutions, but whenever we get our answer, we can do our conversion factor. Okay, so let's start solving, right? And so if we write down what we know that our initial velocity is 0 radians per second, because before the fish jumps on, it's not moving. We know the angular acceleration is 110 radians per second squared. We know the time is 2 seconds. And then what are we missing? We're missing, I wrote V. You're going to see that happen a lot in this unit. I'll write the wrong unit. So we're missing omega and delta theta, but we need this in revs, not radians. Okay. So let's figure out some of these. Let's go ahead and start solving, right? So for the first one, we're trying to find the final angular velocity. So I've got omega, alpha, t, and I'm missing omega. What's the one in this part of the question that I'm not asked for, not given, is the delta theta. So I'm going to use omega equals omega 0 plus alpha t. And before I start plugging in, I can cancel that out. And so that becomes omega equals alpha t. So omega will be simply 110 times 2, or 220 radians per second. Okay. So that's part A with the final angular velocity. Now we could use that if we want to, or we can just simply, assume that this is wrong and move into a separate equation. So in the second one, I have that. I have omega 0, alpha, t. Now I'm looking for delta theta. So what's the one equation what are we missing that we don't care about again? Is in this case would be final velocity. So what am I gonna what equation am I going to use? The only equation that doesn't have final velocity is delta theta equals omega 0 t plus 1/2 alpha t squared. But just like before, that's 0. So all I'm really looking at is the 1/2 alpha t part, right? 1/2 alpha t squared. And so delta theta equals 1/2 times 110 times 2 squared, okay? Which will give me the same answer as my omega, but I'm not looking for it in rads. I'm looking for it in revolutions. So what I now have to do is say, now I have to use my conversion factor. So 1 revolution is 2 pi radians, or 6.28 radians. And so really I'm just doing 220 over 2 pi, and it ends up being 35.0 revolutions. So that's how many times that reel is going to spin in the 2 seconds that the fish is on the line. Now, they threw this 4.5 seconds in there because maybe they say, okay, how much string is pulled, right? So if they ask you that, that's when you can use just simply your V, or sorry, not V, but you would use X equals R theta. And so then you would do 0.045 times 220. Now remember, in this equation, there you would have to use your radians measurement, because our SI unit is radians. And I need to do this quick calculation because I didn't solve for this because it was just a simple add-on. So, I mean, if you think about it, that fish pulled almost 10 meters of string out, which is okay because there's almost half a mile of string on that reel right there. So it's all good. All right. Now, in the next video, we're going to look at rotational dynamics, because it kind of follows along what we do, right? Kinematics to dynamics. And then we'll finish the unit up with angular momentum.